right, so thank you all very much for coming to today's colloquium. So as you will have seen in Peter's email, we have a guest today. Our speaker is Tom Haworth from Queen Mary University of London. He did his PhD in Exeter and then moved to London, or to Cambridge, where he did a postdoc. Then was a junior fellow in Imperial College and is now at Queen Mary University, a Dorothy Hodgkin Fellow and reader in astrophysics. His work over the years has focused on various ways that the cluster environment affects and actually destroys the disk in which planets form. Mostly through models, but also through observations with instruments like JWST, Hubble, with MUSE. And so, yeah, I think today we'll talk about planet formation in stellar clusters. So there should be a broad talk, and hopefully also, I think you said, friendly for planet experts.
I hope so. So if there's anything that isn't making sense, that we can chat as we go as well. I'm quite happy for questions as we proceed.
But with that, I think, yeah, let's wait for one last person to enter our group. And yeah, let's begin.
Thank you. Okay, yes, so thanks for the nice introduction. Saved me a bit of talking about myself there. I just want to point out that the only reason my career has been so UK-centric is the two-body problems. I've been very lucky in that respect. It's not that I'm scared of going to other places, and it's lovely to be being Graz. This is my first visit, and I'm really liking the city, and the department here is lovely. So thank you for the invite. So come on, there we go. So I wanted to just start off by pointing out that this is a field that is both old and new. So people have been, the study of star-forming regions, normally disks were studied in the context of those from early on. So we'd have surveys of the star-forming clouds, and the disks would be studied indirectly as part of that a lot of the time. And then we had images, as I'll show in a moment, a higher resolution with instruments like Hubble that showed a direct impact on the disks. And then there was a gap in the middle where ALMA changed things and our view sort of got smaller scales, and now it seems to be going out to larger scales again and thinking about the star-forming context. And so while the number of people working on the star-forming environment and its impact on disks sort of dropped for a while, it has recently ballooned again. And this is a picture from a workshop that I organized last summer with some familiar faces here. And so rather than put up an acknowledgement slide, I just wanted to point out that everyone here is contributing to the work that we're going to show today in one form or another, and there's many other people also not included here. So it's really great that this field is expanding rapidly, and there's a very friendly, nice community, and we're all collaborating a lot as well. So what is the motivation? Well, as many people, probably everyone here knows, we're now discovering many exoplanets. I forget what the latest count is. And they're incredibly diverse in their properties, typically unlike the solar system, and we want to understand why. And I'm just illustrating some aspects of that diversity. So this is planet mass, orbital period, space. So how massive the planet is compared to Jupiter. There is Jupiter. And this is the orbital period, which is a proxy for how far away it is from its parent star. And you can see we have many different types of planets. There are hot Jupiters. There are molten small planets at small radii. There's Earth-like planets. There's ocean worlds, ice giants, and cold Jupiters at larger distances. And this diagonal dashed line is pretty much the detection threshold that we have. So it's not that there are no planets down here. It's just that we struggle to find them. And so you see planets pretty much everywhere you look, with some interesting features like this gap here. And in addition to having lots of different kinds of planets, we also have different planetary architectures per system. So this is a histogram showing the numbers of stars with different types of planets. So most have one known planet, but we are getting up to larger numbers of planets per system. And then this is the planet radii as a function of the star mass. So maybe there's some sensitivity to the stellar mass. We also see evidence for sensitivity to metallicity, to all sorts of other parameters. So the main message I'm trying to communicate here is planets are really diverse. And planetary systems are diverse too. And so if we want to understand this, we're going to need to do two things, I would argue. One is understand how the planets form in the first place. Perhaps that something intrinsic there instills diversity. And then we also need to look at how they evolve once they're formed. So that how they evolve once they're formed could be important for that valley, that gap of planet properties that we see at small radii and intermediate, small orbital distances and intermediate size, as for example, the atmospheres may evaporate. But I'm more interested at the minute in the former. So what is it about the formation of planets that maybe gives them diverse properties? And so how do planets form? Again, this is probably not new information to most of you, but we now have pretty overwhelming evidence that they form from flattened disks around young the same direction. And so when you see a flattened disk of material orbiting the star in a plane, it's the natural place to form planets. So this is obviously just an artist's impression. This process takes potentially 250,000 years or more. So these disks are left over from the star formation process and are what produce the planets. And I mentioned ALMA a minute ago, but this is a facility in the Chilean desert. It's an interferometer that lets us study these disks in the sub-millimeter and millimeter wavelengths. It's really revolutionized our view of these disks. So the first image of a circumstellar disk with ALMA came out in 2015 when I was at the Institute of Astronomy in Cambridge. This is HL Tau. And I remember the excitement that this caused because it wasn't released as a paper first, it was a press release. So there was it was on the internet with a JPEG image, and this was our first view of this, and we had a sort of emergency meeting, and we're getting our rulers out, trying to figure out what the separation was between these, and using the RBG pixel values to try and understand how the gaps were. So we've gone from this view that we had previously that I'll show in a minute of disks maybe in silhouette, where they look fairly continuous, to this view of what we're probing here is dust, so solids towards the midplane of the disk, which seems to have all these gaps. And this caused problems at the time because if you put a planet in each of those gaps to carve them out, then you pretty much broke planet formation theory at the time. And it turns out HL Tau is not a unique object. So this is from the D-Sharp survey, again looking at the dust in many disks. There's 20 in this image. And again, the rule seems to be that you see substructure. So ALMA had a massive effect on our view of these planet-forming disks. We can even actually see the planets themselves in rare cases. So this is PDS 70. You've got a great big cavity in the disk, and if you zoom into that box there, you can actually see a young planet, which we also see as accreting, because our arguments about the planets going around in the right direction and in a plane in the same direction, and disks do that, is one thing, but here we actually see the planets, so yeah, we're certain the planets are forming these disks. And theoretically, even prior to ALMA, people were modeling planets within disks and looking at the effect they had on the surroundings. So this is from Claire Nelson. And so the planet here is again accreting from the surrounding disk, clearing a gap, and also inducing a bunch of structures in the disk. And the ALMA observations themselves also stimulated lots of further modeling efforts. So with that image, that movie we were just looking at is a gas-only simulation. But these images are of dust, as I already said. And so people following these observations started to do a lot more dynamically decoupled dust-gas simulations. So what we've been doing is on the left, the gas evolution, and on the right, the dust. And there are just, I think, 2 planets in this model. And they're able to induce multiple ring features in this simulation. So ALMA has been fantastic for the study of planet formation in disks. We're now able to peer deep within them, learn a heck of a lot more about planet-disk interaction, and the structure of these disks. But there's a bit of a caveat, I would argue, which is that ALMA is an interferometer. And so it filters out large scales. The higher your resolution, the smaller your larger scales are too. So every single image here looks isolated, right? It's a disk in a dark background, against a dark background. Right? It's nothing out here that could be affecting the disk. But in many ways, it's now becoming clear that the wider environment appears to matter. And so that's what I want to just give an overview of at first in this talk, is the various ways that the environment could affect these disks. And it's also not going to be exhaustive. I don't know if anyone here works on cosmic rays, for example. I'm not really going to be mentioning those, but so environmental impact. So one way you can affect the planet-forming disks is through tidal encounters, gravitational interactions with other stars. So this is a simulation from Matthew Bate. We've got a disk around a star here, and through interactions with other stars in the cluster, the disk is basically going to be completely destroyed in this little simulation here. I don't know if we have what the time scale is, but you have disks losing material, disks stealing material. These are very sort of dynamically complicated structures. Oops, let's watch it again. It's a nice little movie. So, and when we look with ÖAW, we only see these sorts of systems at a snapshot in time, and we are filtering out this large scale gas as well. But, and I'm not really going to go into this, these flybys are generally expected to be quite rare. They should happen early on in the disk's lifetime, but typically, as the cluster starts to dissipate, they get a bit rarer. This is just another example of a flyby. This is a very cool one called RW-Auriga. This is a moment one ALMA observation of the system. So you have a star here with a disk, a star here with a disk, and this large tidal tail. And at the bottom is a simulation of what we think happened in that case. So the star flies by, interacts with it, and induces this large tidal tail, and also steals a bit of a disk too. But again, these are thought to be relatively rare. There's been some papers in recent years saying that these tidal interactions are common, but those mean an encounter within 1,000 AU, which actually doesn't do that much. But if you want to get to this sort of distance, 100 AU or so, then they're pretty rare. Okay, so you can have other stars and their gravity affect your disk. One of the hot topics at the minute is infall. So you don't just have stars forming big groups from collapsing clouds. There's not just other stars there, there's also gas. And so there's a lot of attention at the minute on what people are calling streamers. So here you have a disk. There's a zoom in on the disk there. And you have a red-shifted filament of gas that appears to be falling onto the disk, and a blue-shifted one down here. And these are starting to be detected in many systems in nearby star-forming regions. And the idea is these can fall onto the disk and replenish the disk of material. People use the term rejuvenation. So you have a disk that's evolving, it's making planets, it's dumping material onto the star, and you can maybe replenish the disk of material. Andrew Winter, who's now at Queen Mary as well, had an interesting paper where he looked at the possible impact of what's called Bondi-Hole Littleton accretion onto young stars. So this is a star just flying through a medium. You've got these velocity vectors here. And if the star was static, then the infall would be spherical. But because it's moving, you get material sort of falls into the wake of the star as it tries to fall onto it. And interior to some critical distance, it can still accrete in this Bondi-Hole accretion paradigm. And you end up with this trail of gas as well as this happens. But what he's done here is predict how massive disks should be, what their accretion rate should be, as a function of their star masses for different ages of cluster and different types of stellar cluster. And his model is the color scale, and the points are the observations. And so he's arguing, though I think it's quite controversial still at the minute, that you can pretty much explain what appears to be the disk masses and how the stars are accreting based on the environmental gas that the stars are sitting in. And actually, this could be a real dominant thing, that material's falling down onto the stars and the disks and really driving the evolution. And just because I've got to plug my own work a little bit. So I had a paper this year where it doesn't come out that well on the screen, where we thought we might have seen one of these sort of Bondi-Hole Littleton accretion trails in Orion, perhaps. Okay, so you can have stars affect the disks, you can have infall affect the disks. I'm going to mention this one only briefly, but you can have other sorts of enrichment. So for example, if a supernova goes off, of course that can affect the disk, because you're going to blow away some of the material. You also chemically enrich it with things like short-lived radionuclides, like aluminium-26. And there's been some nice work by Tim Lichtenberg and others on the impact of this. So, because this heats solids in the disk effectively, they end up having less ices. And so he has some papers saying that if you put if you try and make your planets in a massive star-forming region where supernovae are going off, then you end up with pretty much with typically drier planets than if they're in some calm, quiescent environment where there's not as much of these short-lived radionuclides, so maybe more favorable to ocean worlds. And then getting on to what I actually typically work on these days is the radiation environment. So most stars most of the disks that I've shown you so far are in a low radiation environment. They're in a cluster of maybe 100 stars or hundreds of stars, and there's nothing particularly massive there. So the radiation field is weak. But if you have a massive star, as we'll see over to the right, then the disks end up taking on a very different morphology, almost like a teardrop shape or a cometary shape. So this is just an artist's impression. We have the disk here, and its material streaming away due to the irradiation of the massive star. And this is one where the zoom doesn't really do the animation justice. But yeah, you've got material streaming off of the disk due to the radiation from this star. And this is just an artist's impression, but we can do better than that. We can actually see these things in reality. So these are real observations with μ's on the VLT of some of these evaporating disks. So got a laser pointer, but like a stick. So this is Theta 1c, it's an O star. And you've got inset here lots of different disks, and you can see that they take on this cometary morphology that we just saw in the movie, and they're all pointing accusingly towards the massive star that's irradiating. Okay. So we do see very unsubtle evidence for disks that are losing mass because they're being irradiated by massive stars. And we also have, in addition to direct observations of these disks with mass loss, we have really nice indirect evidence as well. So looking at the statistics of disks in clusters, so we can look at things like how massive do we think the disks are as a function of their environment, how large are they. So there's some very nice work from Siak here, from the solar survey, looking at the median dust masses of disks as a function of how strong the radiation is. So those nice pictures we just saw are sitting over here on the right, where the radiation field is strong, and as it gets weaker, there seems to be a continuous increase in how massive the disks are. So this is quite cool because it tells us that you don't just need to be near an O star to have an effect of the radiation on the disk. Even down to weak UV fields, what the radiation environment is matters. And people have also been looking at the chemical impact of external irradiation. So that's some of the stuff we've been talking about here. This is a very limited slide compared to the reality of what everyone's doing. But this pair of disks has been looked at a lot. So there's a JWST survey from a team called PDRs for All that have spent a lot of time looking at this disk. I believe it was the first detection of this important CH3 plus molecule, but there's been lots of other chemical studies too, and people are also starting to look at this one a bit more as well. And there's others looking at the composition of irradiated disks in distant clusters too. But there's lots more to come on the chemistry of irradiated disks, as many people here will be working on. So yeah, this is the first sort of phase of the talk, is that there are lots of different ways in which these planet-forming disks are not isolated systems. They can be affected by gravity of other stars. They can be affected by the surrounding gas. They inherit, I haven't really mentioned this, but like the metallicity of the disk depends on the cloud they formed on. There may be supernovae going off. I didn't mention at all cosmic rays and magnetic fields. They could also play a role. And then the thing I'm mostly focusing on is this external radiation. So I was always told in a 15-minute talk, people should remember one thing at best about you. So the first main message for this talk, I'm going to be ambitious and try and have 3, I think, is that if you forget everything else, that I think there's this connection from the planet formation scales, certainly to the star formation scales. And given star formation regions are actually also a function of the galactic environment, there's probably this large-scale connectedness between the planet formation process and what's going on at the galaxy scales. If you have a starburst galaxy making tons and tons of stars, then you're probably going to get quite different planets to if you're making your stars mostly in quiescent low-mass clusters. Okay. Any questions up to there? It's a good natural stopping point now. No, I can continue. So what I wanted to do today was just a few things if time permits. So the first one, so we're now going to really turn our attention to that last process, the photoevaporation, the radiation environment and how that affects the disk. So the first thing we're going to look at is how, in a very simple terms, it operates. So what is it about shining light on a disk that makes it lose mass? In a very simplified way. And then they're going to ask how often we expect it to be important. This is the one I will kill if we're running out of time, but I was going to just give a quick overview of some of the ways we're trying to look into this problem within the group that I'm working with at Queen Mary. And then we will do this. This is the title of the talk. We'll then look at how it might actually affect planet formation. So number one, how does this external photoevaporation operate? This is my only equation or two in the whole talk. So if you were to have a mass and have material around it at some constant temperature, the mean thermal motions of particles in that gas, they're going at the sound speed. And if you were to extend this medium at some constant temperature out to large enough a distance, eventually those sound waves in the gas are going to be faster than the escape velocity you need to become unbound from this mass. Okay, and so if you compare the speed of sound with the escape velocity you need to be unbound from the star, you can get something called the gravitational radius. So if we had this constant temperature material, be it a disk or a cloud, then beyond this line that represents this gravitational radius, the gas would just be unbound. Just the motions of the particles unbind themselves from the star. And so the idea of external photoevaporation is where you'd have a disk that is otherwise stable, so it's smaller than whatever your gravitational radius would be, but then you shine ultraviolet light or some other energetic light onto it, warm the disk up. So if you boost the temperature, the sound speed goes up, this gravitational radius goes down, and make a disk lose mass where it otherwise wouldn't. So that's the very simple terms idea of what's happening. It ends up being slightly different to this, but basically you're just warming up material enough to gravitationally unbind it from the system. And the way it affects the disk is in two main fashions. So this is these plots show how far away you are from the star. So the star would be, this is the central star that the disk orbits. The star would be here and here. And then this is how much material there is at a given radius from the star. Okay. And the color bar is time. So we shine light on the disk. It typically loses material from the outer regions. If we're in a very low UV environment, the disk just pretty much uniformly depletes. It truncates a little bit, it can even expand. And it's just accreting material onto the star and getting slightly lower mass over time. If we externally irradiate the disk, we deplete material from the outer disk. It truncates, so you can see it's smaller. This is maybe 200 AU here, whereas this is rapidly shrinking into like 20 AU. And it's also lower mass. So the two effects of this external radiation are truncation of the disk and depletion of the mass. And you ultimately end up also with a shorter lifetime. This one's lived for 10 million years, and this one's lived for maybe 1 million years.
But it assumes that there once was a more extended disk when this UV radiation was always there. Maybe it was never bound, actually.
Yeah, sure.
So the outer layers might be actually an artifact. Considering them.
Yeah, absolutely. Yeah, so we don't know the initial conditions of disks. And one of the things I'll mention in a second is this really matters. So the cartoon schematic of what the external radiation does. So if you take a disk and shine UV light on it, you end up with less mass, smaller disk, and less time perhaps to form your planets. Okay, so we'll look towards the end of the talk of how that might actually matter in practice. So now let's think about the prevalence of this external photoevaporation, which ties into initial conditions, right? If disks were born tiny and stayed tiny forever, then it would never really do anything, because you have to be large enough that you are beyond this gravitational radius. So this is showing different star-forming regions. So we've got Taurus and Lupus. This is where this is Taurus, this cloud. So this is where many of our observations at high resolution with ALMA have come from. They've ordered hundreds of stars. Now, those beautiful teardrop-shaped evaporating disks are in the Orion Nebula cluster. But then we have these much larger clusters, like the Arches, Western One, and the Tarantula. And so if we want to have a full understanding of how this irradiation operates, we need to understand what happens in different types of environment here. Now, there is a what's called a cluster mass function, which describes how many of these kinds of clusters you expect compared to these ones. So you basically end up with lots of these and not many of these. And what we've done in an exercise here is randomly sampled stellar clusters from that distribution. And then whenever you get a randomly sampled cluster, you can also randomly sample the distribution of stellar masses you expect from something called the initial mass function of the stars. And when you do that, you get a distribution like this. Okay, so this is how much far ultraviolet radiation there is from all the stars in the clusters. So when you have small clusters, there are many of them, but they typically don't contain a massive star. So occasionally you might sample this and be lucky enough to pull a massive star and get quite a high radiation field, but typically they're quite low. But when we get to these massive clusters, you consistently always get lots of radiation. And what the color bar here is showing is that for every one star in the gray region, if you look at the overall number of stars you sampled, you expect 10 in the orange and 40 in the blue. So this is critical for the context here, in that if we are with ALMA looking at Taurus and Lupus, we're looking at pretty unusual disks probably, right? Because they're in low UV environments. Most stars, when you sample this distribution, we expect to be in these stronger radiation environments. And even Orion is sort of only sitting at the tip of the iceberg here in this sort of most commonly populated region. So we really need to understand how these more extreme clusters work, and that's something that I'm quite interested in now. But you know, that was just adding up all the stars and ignoring the complexities of star formation. This is from the Star Forge group simulations. I think led by Mike Rudrich, or certainly he made this model. So you've got a cloud collapsing here to form a cluster of stars. There are no massive stars here yet. The jets are currently dominating the feedback, driving lots of momentum into the surroundings. And eventually the movie will pause for a second, and then a massive star will turn on and start blowing away the gas. And the point is, at this stage, there is no external photoevaporation happening. There's just low mass stars. So if you're trying to make planets at the minute, then you're getting a nice head start on whatever the impact of the evaporation will be. Okay, so then we paused, and now you can see the gas starting to get blown away. In a minute, there'll be a great big hole in the cloud. Okay, so we can do experiments like take a disk and shine light on it and see what happens. But actually, this connection to star formation is really messy. You know, stars are born typically embedded. They're going to have some time to start making their planets before they get irradiated. And so understanding this connection from the larger scales to the smaller is something we really need to do more. So now any disks in here are going to be getting destroyed very quickly. And this comes back to your question a little bit earlier, right? It's a complicated history. So the second message, so number one is that planet formation is probably not an isolated process. It depends upon the star formation and the galactic scale, probably. So the second message is that this radiation of the disk does affect the disk's evolution. You know, it shrinks it and depletes it. Many stars, so there was that blue region in that distribution plot, many stars will form in regions where the radiation field is strong, but that doesn't mean they're necessarily irradiated by a strong field, because they could form in a very embedded fashion and stay shielded from the radiation for quite a long time. So this is something that's a big unknown. I think we do have time to have a quick, it's only past. So I think we'll have a bit of time to quickly look at what we're doing at Queen Mary. So I'm lucky enough at the minute to have it's a double-edged sword because it's hard work, but I'm lucky enough to have quite a few people working with me at the minute. So we'll be talking a bit about what Lynn did on the planet formation side of things. We've got a couple of other PhD students and luckily quite postdoc heavy, so most people are quite independent. I'm going to try and give a bit of an overview of some of the things we're doing. So my history in the study of irradiating disks was mostly on simulations. So taking disks and irradiating them and asking how much mass they lose and from where in the disk. This is an image that's not published yet. I don't know if and when I'll get around to working on this stuff in more detail, but here we have a planar radiation field coming down upon the disk from up here. It's a 2D axisymmetric model. And on one side of this line, I'm just plotting the density structure and here the temperature. I've also sort of excluded all the emission out here just to keep it simple. And you can see the velocity vectors here as well. So we shine light on the disk, it loses mass. And you can look at things like simulated observations from this. So this is a simulated Paschen alpha observation of this model and a real one from the James Webb Space Telescope. So I'm interested in connecting these models to observations. And Tiger Peak is a PhD student who has been working more on sort of the ionized gas diagnostics of these topographic winds. Julia has finished with me now, but she was also looking at again, observational diagnostics, trying to identify these evaporating disks in very distant star clusters where we can't see this cometary shape. And so looking for things like how does certain emission lines vary as a function of the radiation field strength. So sorry, this is the ratio of the oxygen 16300 angstrom line to the accretion rate. And so in a low UV environment, we expect it to take a pretty constant value. And then when you get to strong radiation environments, it explodes. So if you want to look in, if you want to ask, can we find evaporating disks in this kind of region, which is far away? Maybe a thing you could do is try and see if this ratio is right, for example. Sebastian Payne is a PhD student who's finishing up next year. So he's been taking these sort of simulations of evaporating disks and looking at what happens to solids, little grains of dust in the wind. So he takes simulations, plots different dust trajectories for different sizes of grain, looks where the dust goes, what the dust to gas ratio is in the wind. And we're now going to be comparing these models to observations of real disks where you see these sort of streaks of dusty material coming out the side, which are quite consistent with these models. So this is from like last week, a simulated observation at the same wavelength as this one. Then we're also thinking about the chemistry, which is, I think, stimulated part of the reason for the visit here today. So Luke Kite, he's been looking at disks and you irradiate them and looking at what the impact of the wind itself is on the chemistry. So here he's comparing things like CO, CH4, CN, HCN, abundance maps with and without the wind. How you define what is wind and what is disk gets complicated, but just for an exercise here, he was comparing what you get, and here he's comparing the fluxes you get for different molecules you might see with ALMA, and it can make, this is nearly 10 orders of magnitude. So, and the thin lines are the models with the wind and the thicker without. So it can make quite a big difference to the fluxes you see. Raphael Mashak is also looking at the H2 chemistry, which we should maybe talk about at some point. And then, yes, so coming back to this issue that the stars form may be embedded, this is what Lynn Tsao did for her first project in her PhD. They're taking star-forming clouds that are making lots and lots of stars represented by the sync particles here, and asking how long do they stay embedded? You know, do they get 2 million years before they get shone upon? In which case they probably make all their planets, and we can go home. And you know, it's just a little detail, the external photoevaporation. It doesn't do anything else. And so she could look at things like the UV field they experience over time. The difference between these lines basically shows you how shielded they are. So this one's shielded for 500,000 years, maybe 0.75 million years, for example. And you can look at the effect that has on the disk. So if you don't shield the disk with the cloud, then it gets destroyed quite quickly. And if you do shield it, it stays larger for longer.
What kind of cloud do you refer to? So is that the direct wind that forms again a cloud, or?
I'm referring to the molecular cloud here. So this is a Carina-like cloud. So, you know, the actual, the natal cloud of the disk.
Is there dust in those?
So here we're doing Monte Carlo radiative transfer to get the UV radiation fields. So you can imagine if I put, let's say, I forget what red and white are here. I think white might be the massive stars. Imagine I had some massive stars in here and I put another star out here, then it's going to be shielded by all the intervening gas. In fact, so this here is where the ionized gas is. This is basically the H2 region. So all these disks out here would be shielded, and these ones in here would be irradiated.
So it's the gas that does the shielding.
Yes, well, and dust, yeah. But we're not considering shielding from the wind of the disk, but it's just the white star cloud. And so, yeah, I'm increasingly becoming a bit of an observer as well. So maybe not very good at theory or observations, but it's fun to work on a bit of a mixture of stuff. So these are some observations in Orion. This is some new stuff in Problem 14, and these are in NGC 2024. So using lots of different instruments to try and find and understand these in operating disks better. Okay, so we will finish, I think, with plenty of time. I wanted to finish off by looking at what this does to the planets. So we had this cartoon earlier. You take a disk and shine light on it, you lower the mass, you make it smaller, and you lower the lifetime. Well, what does it do to the planets? Well, there's been a few studies now, but two main ones that try and just understand phenomenologically what will happen. So I want to summarize them first with a cartoon, and then I'll show this more science grade plots. So the first one's to do with the growth and migration of giant planets. So here we have the star, and here we have the disk. So both of this one starts by saying we don't know how the planet got there in the first place, but something put it there, right? So maybe gravitational instability. There's something puts a planet seed at large distances. Okay. So this is the mass of the planet and its distance from the star. And we know that giant planets, if you form them out here, will accrete from the surrounding gas and eventually get massive enough that it can migrate through the disk, so they can continue getting more massive, and eventually they'll move into the inner regions. Okay. And the other planet formation scenario is by pebble accretion. So in this one, you have some sort of planetary embryo in the inner disk, and dust is going to get bigger and grows over time, right? And eventually it can get big enough that it moves inwards. Okay. So the reason for this is the dust is always orbiting at Keplerian speed, but the disk also pressure supports itself, so it goes a bit slower than Keplerian. So the dust going at Keplerian speed is being slapped in the face by gas constantly and loses angular momentum and drifts inwards. And so that can get accreted by the planet. And that process happens from the inside out. So dust grows and drifts, grows and drifts, grows and drifts, grows and drifts. Okay, so we'd have what we call a growth front, moving outwards to the outer disk, and over time this flux of pebbles continues. And so here you have a planet in the inner disk that would grow by accreting these pebbles and maybe drift a little bit. Okay, so when I was applying for grants, I remember getting asked outer disk, so why do we care? So these experiments will show why we care. So just from a cartoon perspective, if we lose mass on the outer disk in both these cases, well, if you truncate the disk quickly enough, you can shut off this accretion. Okay, so you can strand a large planet out there. In this one, this planet can potentially have pebble flux coming from anywhere in the disk. So by reducing the size of the disk, dragging some of that dust away, you're limiting that potential pebble flux. And here's a sort of version of these two scenarios. So this again is how much, so the host star that the disk is around is always in the lower left here, or on the left-hand side, sorry. That point is here. And again, the lines here are how much mass there is in the disk at a given radius, surface density. And the color bar is again time, and the points are the evolution of the planet. And the radiation field gets stronger as you go down. So when the radiation field is weak, the disk survives for longer, the planet grows and eventually migrates. Whereas when we increase the radiation field, it can grow a bit, but in this case becomes, what is this? About 80 Earth masses, 70 Earth masses or something like this, but doesn't get to migrate. And in the very strong radiation field case, it just doesn't get to do anything because it just gets destroyed so quickly. And then Lynn, in her second paper, did the same for pebble accretion. It's not so nice a representation as that previous plot that I have to hand. But what I want to just point out that one of the key things she also looked at was this idea of a shielding timescale. So you'll make your star when a cloud collapses. There's the star with the disk. It's not immediately irradiated. It will be in there for some time. Okay, so what she's showing here is this is how long the disk is shielded for, how long it stays in its birth cloud before it gets shone upon by O stars. This is the final mass of a planet that had a seed put in at a certain radius in the disk. And this is where the final orbital radius is of the planet. So the key thing here is if you shield your disk for 3 million years, say, then or even just for maybe 1 million or 1.5 million years, then your planet masses don't seem to care about the external radiation. You can, your planet formation gets going and the planets manage to grow substantially before the radiation does very much. It just destroys the outer disk. But the absolutely critical thing is this first 500,000 to 1 million years. Okay, there is a hugely non-linear sensitivity of the planet's mass. There's a few orders of magnitude potentially, change in the planet's mass depending on exactly when you irradiate the disk. So if you're interested in exoplanet diversity, then these shielding timescales could be really important. And there's a nice little example here, an anecdotal example from this plot, which is what for one of these, if you don't shield the disk at all, you end up with something that's lunar mass between the orbit of Uranus and Neptune. But if you take the same model and shield it for 1 million years, you get a 1 Earth mass planet at 1 AU. So based on these sorts of results, one of the things I'm really interested in now is finding young star-forming regions with evaporating disks. If there are some that are thought to be about 500,000 years old, so any disk evaporating, you would say should be competing with planet formation. Anyway, so pretty much done. So final takeaway messages. I think this is summarizing everything here. So number one, not just external photoevaporation, but infall, stellar flybys, chemical enrichment, supernovae. The planet formation process and disk evolution is likely affected by the environment. And a lot of stars, and hence disks and planets, will form and evolve in quite massive clusters that don't look like the ones that are nearby to the sun. And hopefully, I mean, they're just numerical experiments, really, what I showed you at the end, but we are starting to be finding some evidence that we expect that the planets do care about this process too. So I'll stop there and happy to take any questions.
Another, I mean, maybe, I mean, it was anyway talked, but I think another interesting effect or important effect is from the external photoevaporation. So when you have other stars and so on nearby a disk, that the gas part is not living as long as if you don't have this, right?
Yes. So
and then the point is, I think. That you may end up with low mass planets, probably depending, of course, on the host star, but also on the accretion time and so on.
yes.
They may collect, if the disk lifetime, the gas disk lifetime is longer, they can collect a lot of primordial gas and end up as something like sub Neptunes, these super Earths which do not get rid away anymore with the primordial atmosphere. And if you have a lifetime of only 1 million years or so, then you get easier a planet which doesn't grow enough mass inside the gas disk, so that it is not a problem later on with the primordial atmosphere.
Yeah, so these models of the pebble flux do include the gas accretion as well, if the planets get massive enough. And the ones on the giant planet growth and migration, I think purely are the gas. They're not thinking about the dust. So yeah, the gas extraction definitely can matter as well.
But that is, I think, is a crucial thing which we expect in the near future when they discover more and more Earth mass planets. I'm quite curious how many of them may have primordial atmospheres and like Earth or Venus not, or we had it, but it got lost afterwards. But if they grow too much mass, so from theoretical studies, so if you would have an Earth mass in a gas disk, then there's a problem probably that you never get rid of it.
Yes.
If the planet is in the habitable zone. So that's some other interesting thing.
So Lynn has a second paper coming soon, which is like multi-planet systems forming with the N-body interactions and stuff as well. And one of the annoying things she's finding is that, take this with a pinch of salt, I can't remember exactly where it is, but I think the biggest difference, like the biggest imprint on the planet population that the radiation seems to have is in a really hard to probe zone there, which is like slightly higher than Earth mass planets at quite large orbital radii, like 10 AU or something. And so it's quite difficult to be able to say, here is the imprint you should expect from external evaporation. But
I think the question is also about this time scale of gas accretion, right? I think So all the planet formation scenarios require the existence of gas. And once the gas is gone, you can't really form any planets anymore. So the gas is there when the core of a planet forms, but then also I think when you are big enough to accrete gas, and it's actually a fairly rapid process, right? So it's not that you form the planet and then you dilute the gas and then you
Does this
don't
also-
get any atmosphere.
Is this also the case for small planets? I mean, if there's a lot of dust, rocks, or moon or Mars type stuff over and no gas, I mean, would the system then be a kind like an asteroid belt type?
Yeah.
I'm not. I mean, of course, it will not form any Jupiters or whatever anymore. But
There's another question.
Yeah, the question that I have is like, how does the solar system fit in there? Because like in a gas giant phase, you have a gas giant and it travels inward, and you travel inward from, I think, 10 AU or 100 AU.
In the calculations of Andrew Winter, let's have a quick look. So he's starting it at, looks about 20 AU perhaps.
20 AU, right? And the solar system, basically, then the idea is that the gas evaporated quickly enough that the outer gas giant stayed there.
Well, and the solar system's an entire different beast. It's really hard to model, to explain the architecture of the solar system. But it's important to say, I think, that the numbers here, that this was done as a numerical experiment, really, to just show, in principle, you could affect what happens to a planet by destroying the outer disk. In reality, you'd want to, it is just a toy model in a sense, right? How did that 20 AU planetary sort of embryo get there is a valid question. But then we do see wide orbit planets, and we do see features in disks at 20 AU and beyond, which are evidence of planets forming.
But it does beg the question if the solar system is something special, or these kind of isolated things. I mean, this is also like one planet, right? You don't have multiple systems in there. So what would happen if you would have multiple of these objects?
Yeah, so that's a paper that Lynn has now, and it's under review, and it's very interesting actually, because if you took a disk and didn't externally irradiate it, you make lots and lots of planets. So many, in fact, that they keep migrating in and scattering the inner planets either onto the star or out of the system, and it gets really messy. And actually, so she's got interesting plots in her newspaper, like the fraction of planets you lose as a function of the radiation field you're in. And you can actually hit a sweet spot where you retain more planets in like moderate UV fields sometimes, because you don't have as many of these chaotic interactions happening. So it really, the multi-planet nature massively, at some level, it washes out the imprint of the external photoevaporation because the planet-planet interactions start to dominate. But when you get high enough to a UV, it does again leave a mark. So it's, it's an interesting interplay. It also potentially affects the fraction of resonant planet systems too. But that impact is from not many planets have resonance systems to even fewer have resonance systems. So it's quite subtle.
Yeah, thanks. Really nice talk. It was a good review. So the questions, I have several questions. I'll ask one. So it's about the shielding timescale you mentioned. So what exactly depends on, and how does it change across?
So this is Lynn's current work with me as a postdoc. So there were two papers that looked at this. Lynn's took a cloud here, and she looked at the statistics, and sort of the number that came from her paper was, by about 500,000 years in a given star's lifetime, it's probably being irradiated. But then there was another paper by Matti Wilhelm with Simon Portuguese-Svart, where they said the shielding was much longer. And the difference in the models was the virial ratio of the cloud. So people studying feedback from massive stars have for a long time found that if you have a very bound cloud before the stars form, then the massive star feedback is pretty ineffective at dispersing the gas. It takes quite a long time for the H2 region to break out. Whereas if it's if it's less bound, then you disperse the gas more effectively. So what Lynn's currently doing is taking a suite of models of star formation and feedback to explore how this shielding varies as a function of the virial ratio of the cloud. But you can imagine it really depends on the nature of star formation. Yeah.
Usually it's as long as 0.5 million years, yeah?
Well, in her first paper, she did. There's obviously a distribution, but she was for a given star that forms in the model. You can ask what's the UV field it sees over time, and how long does it take to get to a certain UV radiation field. But I think 500,000 years is the number I have in my head at least, which would be interesting because in this plot, 500,000 years is an interesting phase of time, right? It's
Okay, thanks.
the planets you get quite a lot.
Further questions? I might ask one of also quite a few. So thank you again for this. It's a really interesting talk. It's such a wide range of topics that I don't really know where to start. But I guess to continue maybe on Goodman's point, if we have this quite complex environment, and you can shield for like 500,000 years, that changes clearly things a lot. What happens if we add the sort of the large scale interactions like the accretion from the environment into this mix, right? Because if we imagine in these quite complex dynamic star forming clusters that you showed the animations of, if we include this process of accreting from the environment at major ages, maybe you can again sort of, despite having already been exposed to your UV field, sort of give your system a kick and sort of reset it.
Just more like off. Yeah, no, this is a super question. As I mentioned in the talk, this idea of infall is a really hot topic. And so Andrew Winter has done a lot on this recently. He's just started at Queen Mary. I'm trying very hard not to step on his toes, but we're happy to work together a bit on this. So no, it's a fantastic question, right? In a low mass star forming region like Taurus, where people are looking at this effect of infall, I think there is a debate. Do disks just evolve in relative isolation, or is infall important here? Okay? I think that's an active debate. Then you could go to an extreme like the center of this cluster here and say radiation probably dominates. But what is the interplay like? For how long is infall important? Can stars move out and have and be rejuvenated? What happens in somewhere like Orion where you're in the middle? So this interplay between infall and evaporation is almost completely unexplored. So in Lynn's stuff she's doing now, we realize that in addition to getting the radiation field over time that you track in the history of the stars as they move through the cluster, you know the density, you know the temperature, and you know how fast the star's moving. So you can also get a Bondi hole accretion rate. So this is not quite right, but this is one star. We don't know what she's working with simulations that aren't her, so we're dealing with some challenges. But this is here, the blue is in some units, the radiation field strength, and the orange is the Bondi hole little accretion rate. So we could in principle do both. So you get interesting things like it starts embedded, gets irradiated, and then seems to re-go into a cloud and get more material. So this interplay could be quite cool.
My gut feeling was indeed like, and I think this sort of shows that it's like in the early stages when that cloud isn't completely dispersed yet, where you get all those fairly thick filaments and have a large gravitational potential, where you can actually get that stuff where it goes in and out of the UV.
Yes.
It's very cool.
So the hope here, so I think in this paper, I mean, assuming we get it to work, because we have much problems with it, the plan would not be to do full disk evolution or anything, because I think Andrew Winter wants to look at disk evolution within infall. But we could at least talk about the statistics, like what fraction of stars are strongly irradiated and then get replenished and things. That sort of stuff is almost completely unexplored.
Any other questions? So Tom will be here until the end of the afternoon. I should also mention that we are going for dinner tonight. So if anyone wants to join us for dinner, you're warmly invited. There are at least a couple of spots, and I don't think it's a particularly small place that we booked at the table. Let's say we can expand a bit. So yeah, by all means, join us for a social part of this this invitation at the end of the day. And yeah, if you have science questions, further science questions, Peter, what do we have like a specific offer?
You can ask them now. Or...
You can ask them now. You can ask them.
I'm somewhere between here and the top of the stairs, I think, for the rest of the day.
Yes. Thank you very much.